The Gulf of Oman sits at the eastern end of the Persian Gulf's strategic complex, where the narrowing of the Strait of Hormuz opens again into water deep enough to give a surface combatant genuine maneuvering room. It is not the claustrophobic shallowness of the Gulf proper. The bottom is far enough down that the sonar picture has depth to it. The shipping lanes have width to them, and a ship can accelerate and turn without the navigational anxiety of a confined waterway. It is, by the standards of the region, open water. This is a relative term. The Iranian coastline is 130 kilometers to the north. The mobile missile batteries that the IRGC Aerospace Force deploys along that coastline are optimized for exactly the ranges that the Gulf of Oman presents. Open water in this region means visible from both shores, reachable from both shores, and targetable from both shores by systems that have been positioned, calibrated, and exercised against the specific geometry of the waterway they are tasked to cover. USS Normandy had been on station in the Gulf of Oman for 27 hours when the interdiction operation began. The target was a mid-size cargo vessel that the intelligence package had tracked for 9 days from its origin port at Bandar Imam Khomeini through the strait and into the Gulf of Oman on a heading that had no plausible commercial explanation. The vessel was not heading for any of the Gulf of Oman's commercial ports. It was heading southeast at reduced speed on a track that, if maintained, would eventually reach the approaches to the Arabian Sea. The intelligence assessment of the cargo milestone developed from signals intercepts, a positive identification of the shipping company as a documented front for IRGC procurement logistics, and the vessel's behavioral history of operating outside shipping lanes and with inconsistent transponder status, concluded with high confidence that the hold contained advanced ballistic missile propulsion components, not assembled weapons. Components. The distinction mattered legally and did not matter strategically. The boarding authority had been granted. The Normandy was positioned to execute it. At 2:33 a.m., the Normandy began her approach to the target vessel. The range was 11 kilometers, closing at 15 knots. The boarding team was staged in the well deck. 8 personnel in VBSS equipment, their rigid inflatable boat rigged for immediate deployment. Their communication links with DC Central and the bridge checked and confirmed. The Normandy's sensors were in full active mode, the SPY-1B sweeping the air picture out to its maximum range. The hull-mounted sonar in active mode addressing the underwater picture. The surface search radar maintaining the track on the target vessel. And the background shipping traffic in the area. The background shipping traffic in the area was denser than usual at 2:33 a.m. Not unusually dense, the Gulf of Oman carried commercial traffic at all hours. But on the upper end of the distribution for the time and the track, the intelligence team had noted the density in the watch log at 2:15 a.m. without elevating it to a specific warning. Because commercial traffic density in the Gulf of Oman at night is not an anomaly. It is the environment. What the intelligence team had not noted at 2:15 a.m. was that 3 of the vessels in the background traffic picture had been on station. Not transiting, not moving on their declared routes, but holding position with minor variations consistent with a vessel maintaining a geographic point rather than proceeding on a voyage for between 2 and 4 hours. The positional analysis that would have identified this pattern required correlating the current positions with the track histories of each contact over the preceding 4 hours, which the navigation team was not running in real time because the standing procedure for background traffic analysis was a manual review conducted at watch change, not a continuous automated correlation. The Iranian Ra'd-500 had been assessed by the intelligence community as a developmental system, a domestically produced supersonic anti-ship missile whose existence had been publicly announced, whose design characteristics had been partially characterized through open-source analysis of Iranian defense industry publications, and whose operational deployment status had been assessed as probable but not confirmed in a forward coastal battery configuration. The assessment carried a caveat. The characterization of the weapon's seeker architecture and electronic countermeasure capability was based on incomplete information, and the probability that the system had been operationally deployed earlier than the assessment's timeline predicted was rated as non-trivial. The Ra'd-500 is fast. Its cruise speed in the terminal phase, the phase where its seeker is locked on the target and nothing in the engagement can change the basic geometry of the approach, is above Mach 2. At Mach 2 and above, the time between radar acquisition of an inbound contact and warhead detonation against the hull compresses to intervals that the human decision cycle cannot match. The Aegis system's automated engagement mode exists specifically because of this compression. Because a supersonic inbound at close range cannot wait for a human to review the track data and authorize a weapon release. The authorization must be pre-delegated. The system must be allowed to engage automatically within defined parameters. The defined parameters represent a balance between the risk of engaging a non-hostile contact and the risk of not engaging a hostile one. And the balance point of that trade-off is among the most consequential decisions that the commanding officer of an Aegis ship makes before an engagement begins. The Normandy's commanding officer had set the Aegis engagement mode to Auto Special, the mode that allowed automatic engagement of inbound contacts meeting specific threat criteria without requiring individual authorization for each weapon release. He had set it 4 hours ago, when the watch picture had been assessed as elevated threat, and he had not changed it since because the threat assessment had not changed. At 2:33 a.m., with an active interdiction approach underway and the full attention of the ship's sensor suite directed toward the target vessel, the auto special setting was the correct posture. At 2:34:11 a.m., the SPY-1B detected a contact, not from the direction of the Iranian coastline, not from the north, where the known coastal batteries were positioned and where the threat picture had been oriented, from the west, from the direction of one of the 3 vessels in the background shipping picture that had been holding station for between 2 and 4 hours. A fast, accelerating contact at low altitude, inbound on a direct bearing to the Normandy's current position, with a velocity profile that the track filter updated in 0.6 seconds from possible surface contact to confirmed supersonic airborne inbound. The Ra'd-500 had been launched from a concealed launcher aboard a stationary vessel in the background traffic, a platform that had been holding its position for 3 hours and 14 minutes, waiting. Not waiting for an order, waiting for the Normandy to close to the range that the Ra'd-500 seeker could acquire from, and then waiting for the engagement window that would minimize the time available for defensive response. The Aegis Auto Special mode engaged at 2:34:11 a.m. The SM-2 extended range fired at 2:34 and 12 seconds a.m. 1 second after detection. The fire control solution had been computed in the 0.6 seconds of track filter processing, updated in the 0.4 seconds of threat assessment, and translated into a weapon release command in the time it takes an electrical signal to travel from the processing unit to the VLS launcher. The SM-2 was in the air before the watch team in the CIC had fully processed what they were looking at. The SM-2 missed. The Ra'd-500's terminal seeker executed a jinking maneuver, a rapid pre-programmed lateral displacement of approximately 12 meters at the point in its terminal approach where the intercept solution's geometry was most sensitive to target position changes. The maneuver was not random. It was designed into the weapon's terminal guidance architecture for exactly this engagement scenario, and it had been timed to occur at the range where an SM-2 intercept solution would be most vulnerable to a sudden position change. The SM-2's warhead detonated 2 meters from the Ra'd-500's right flank, within lethal radius for many warhead types, outside lethal radius for the Ra'd-500's fragmentation pattern given the misgeometry. The weapon continued. The Phalanx had been tracking the contact since the SPY-1B's initial detection. The system engaged at a range of 1,400 meters, The 20mm rounds impacted the Ra'd-500's airframe and disrupted its aerodynamic stability, causing the weapon to deviate from its terminal approach vector by 6 degrees downward in its final 400 meters of flight. 6 degrees downward at Mach 2 over 400 meters is a significant altitude loss. The weapon that had been aimed at the Normandy's waterline arrived at a point approximately 2 meters below the designed impact point, 2 meters below the waterline. On the stern, in the section of hull plating that covered the aft machinery space, the space housing the port and starboard propeller shaft bearings, the rudder actuators, and the aft section of the gas turbine exhaust system, the Ra'd-500 detonated at 2:34:19 a.m. The warhead was large by the standard of the weapons the Normandy had been built to defeat. A weapon designed for supersonic delivery against a surface combatant does not need to be precise in the way that a subsonic missile needs to be precise, because the kinetic energy of a supersonic impact adds to the warhead's effect in a way that changes the penetration and blast geometry. The detonation at 2 meters below the designed impact point, below the waterline rather than at it, produced an underwater component to the blast that directed a significant portion of the energy upward into the hull structure from below. The keel in the aft section flexed. The shaft tunnel that housed the port propeller shaft fractured at the aft bearing housing. The bearing housing itself separated from the hull structure at its mounting points, and the port propeller shaft, still spinning at the rotational speed corresponding to 15 knots of ship speed, became unsupported at its aft end. An unsupported rotating shaft at propulsion speed is a mechanical emergency. The shaft's own eccentricity, amplified by the loss of its bearing support, produces a whipping oscillation that propagates forward along the shaft at a rate that, if not immediately addressed, will damage the coupling, the gearbox, and the turbine itself. The engineering officer of the watch executed the port shaft emergency shutdown at 2:34:26 a.m. 7 seconds after the detonation. The port shaft came to a controlled stop at 2:34:51 a.m. No gearbox damage. No turbine damage. The emergency shutdown had been executed before the oscillation could propagate forward to the machinery. The starboard shaft was intact. The Normandy had lost half her propulsion but retained full steerage and the ability to maneuver. Because a single-shaft Ticonderoga-class cruiser is still a maneuverable vessel. The speed loss was immediate and significant, from 15 knots to 7, as the single-shaft thrust was insufficient to maintain approach speed against the hull drag. But the ship was moving and controllable. The flooding was a different problem. The Ra'd-500's detonation below the waterline had produced hull damage at the aft section that the damage assessment team was still characterizing when the flooding alarm activated at 2:34:33 a.m. 14 seconds after the detonation. The alarm came from 2 spaces simultaneously. The aft machinery space itself, where seawater was entering through the fractured shaft tunnel bearing housing that had separated from the hull structure, and the void space adjacent to the aft machinery space on the port side, where the hull plating deformation from the blast had opened a seam along a weld joint that ran diagonally across 2 hull plates in the affected area. 2 flooding sources, 1 critical machinery space, 1 void space. The flooding rate from the shaft tunnel bearing housing separation was the more serious of the 2. Not because the rate itself was higher, but because the geometry of the breach was in the shaft tunnel, which was a penetration through the hull for the shaft itself, and which could not be plugged with conventional patching materials while the shaft remained in place. The shaft had been stopped, but it was still physically occupying the tunnel it had been rotating in, and the tunnel, fractured at the bearing housing, was admitting water around the shaft at a rate the damage assessment team initially estimated at 300 liters per minute. 300 liters per minute into the aft machinery space, which contained the shaft gearboxes, the aft turbine exhaust systems, and the electrical cabling bundles that served the stern section's weapons and sensor systems. The space was not designed to accept flooding at any rate. The equipment in it was not designed to operate in a flooding environment. The combination of flooding rate and critical equipment created a priority that put the aft machinery space above every other casualty on the ship in the damage control officer's assessment. He made the call at 2:34:49 a.m. Isolate the aft machinery space from the rest of the ship's flooding management system and treat it as a primary flooding casualty requiring maximum effort. He committed 2 full DC parties to the space. The primary party through the aft access and the secondary party through the starboard deck access, and tasked the engineering officer's team with assessing whether the shaft could be physically withdrawn far enough from the hull to allow the tunnel to be packed with emergency sealing material. The shaft withdrawal question was the engineering problem that had no simple answer. The port propeller shaft was a fixed length of forged steel connected at its forward end to the gearbox and at its aft end to the propeller, which was submerged. It could not be withdrawn in any meaningful sense without disconnecting it from both ends, a procedure that required dry dock equipment and was not available at sea. What could be done was to pack the annular gap between the shaft and the fractured tunnel with emergency shaft seal material, a rubber compound packing that the ship carried in the emergency repair kit for exactly this purpose, and to apply hydraulic pressure against the packing to hold it in place against the inflow. The shaft tunnel emergency packing kit required 3 operators in the aft machinery space, 1 holding the packing material in position, 1 driving the packing follower with the hydraulic tool, and 1 managing the hydraulic pressure supply from the portable unit they had brought through the aft access. 3 people in a flooding space with 300 liters per minute of inflow and no drainage until the portable pump was rigged and operating. The pump was rigged and operating at 2:36:14 a.m., 1 minute and 41 seconds after the flooding alarm. The pump capacity was rated at 400 liters per minute, sufficient to stay ahead of the 300-liter inflow and begin reducing the water level while the packing operation was in progress. The water level in the aft machinery space peaked at 41 centimeters depth at 2:36:20 a.m. and began to fall as the pump output exceeded the inflow rate. The packing operation took 11 minutes. Not because the procedure was complicated. The 3-operator sequence was documented and had been drilled, but because the fractured bearing housing geometry created irregular surface conditions around the shaft that the packing material had to conform to. And conforming required patience with the packing follower tool that the urgency of the situation made difficult to sustain. The petty officer first class managing the hydraulic tool told himself once, in the 30-second interval between the 6th and 7th driving sequence, that the 11 minutes were already gone and the packing was almost seated, and the water level was falling and the only thing left to do was finish. He told himself this and went back to the tool. The shaft tunnel was sealed at 2:45:41 a.m. The flooding rate from the shaft tunnel dropped from 300 liters per minute to 12, a seep through the packing that was within the pump's management capacity by a factor of 30. The void space flooding had been addressed by the secondary DC party through a conventional hull patch approach. A wooden plug driven into the primary weld seam opening and a backing plate installed over it, while the void space filled to a manageable level, and the portable pump in the adjacent passageway kept pace with the inflow. The void space flooding was declared controlled at 2:43:11 a.m., 8 minutes and 38 seconds after the flooding alarm. The aft machinery space flooding was declared controlled at 2:47:03 a.m., 12 minutes and 30 seconds after the flooding alarm. Combined with the void space containment, the Normandy had addressed 2 simultaneous flooding casualties with primary equipment damage in 12 minutes and 30 seconds from the alarm. The water level in the aft machinery space had not reached the electrical cabling bundles that served the stern systems. The equipment in the space was wet. It was not submerged. The boarding operation had been suspended at the moment of the Ra'd-500 detection. The target vessel, the cargo ship carrying the ballistic missile propulsion components, had observed the engagement and had used the 4 minutes of the Normandy's damage control response to increase its speed and alter course toward the Iranian coastline. It had not reached Iranian territorial waters when the fleet commander's authorization for pursuit arrived at 2:49 a.m. The USS Anzio, positioned 42 miles to the east, was vectored to intercept. The Anzio's VBSS team boarded the target vessel at 5:14 a.m. The cargo was confirmed at 5:47 a.m. The Normandy was taken under escort by the USS Anzio at 6:22 a.m. and began the transit toward the Bahrain repair facility at reduced speed on her single operational shaft. The port shaft tunnel, packed, sealed, and holding, was monitored continuously throughout the transit. The packing held. The flooding did not resume. The aft machinery space remained dry for the remainder of the transit. The transit took 19 hours at single shaft speed. The Normandy arrived at Bahrain at 1:15 a.m. the following morning and was placed in the repair facility at 3:40 a.m. The dry dock survey confirmed the shaft tunnel bearing housing fracture, the hull plate weld seam failure in the port void space, and the keel deformation at the blast point, all consistent with the damage control team's at-sea assessment, which the investigating officers noted in their report as an accurate characterization of the damage made under conditions of active emergency and without access to the underwater survey equipment that the dry dock inspection used. Here are the numbers when the dry dock survey is complete and the repair estimate is on the fleet commander's desk. 3 hours, 14 minutes the launch platform held station before firing. 1 second from Ra'd-500 detection to SM-2 launch by auto special mode. 12 meters, the terminal jinking displacement that defeated the SM-2 intercept. 2 meters below waterline, the actual impact point after Phalanx deflection. 7 seconds from detonation to port shaft emergency shutdown. 300 liters per minute, initial flooding rate through the shaft tunnel breach. 11 minutes to seat the emergency shaft tunnel packing. 12 minutes 30 seconds. Total time from flooding alarm to both casualties controlled. 0 electrical equipment lost to flooding in the aft machinery space. 1 cargo vessel boarded by USS Anzio at 5:14 a.m. 0 fatal outcomes among the crew. The Ra'd-500's development program had produced a weapon that the intelligence community had not fully characterized in time to optimize the Normandy's defensive posture against it. The jinking maneuver that defeated the SM-2 was a terminal guidance feature that the assessment had not predicted. The launch from a civilian platform in the background traffic was an operational technique the analysis had not connected to this specific engagement geometry. Both gaps were real and both would be closed in the assessment updates that followed the engagement. What the gaps had not defeated was the 7 seconds between detonation and shaft shutdown, or the 11 minutes of shaft tunnel packing, or the 41-centimeter water level that never reached the electrical bundles because the pump was running before the water level peaked. The intelligence community learns from engagements. So does the crew. The difference is that the crew learns while the ship is still flooding.